Now we move to the next part, methods of validation for simulation models. Here we focus on conceptual and early validation, meaning how we check the model before heavy data analysis. The key question is simple: can this model already be trusted at this stage? Okay guys, so if you would search for some books or textbooks dedicated to validation and verification, most probably you will find quite complex validation and verification procedures. The problem is the following, which we have already discussed, that performing a validation via spending the time, it increases the costs of a simulation project. That's why it is always the trade-off. Therefore, now I am going to speak about something which is called a three-step approach or three-step validation, three-step framework for a validation, which by my opinion at least, much more orientated to practical application. Okay, so now we are moving to the first stage, and a following stage is focused on high phase validity. We visually check if the model behaves realistically. Using animation, we look for illogical events, wrong routing, or unrealistic use. If experts say this doesn't look right, the model needs a revision. I would like to pay your attention to a following part of the slide. So please explore the following assumptions about the process. And as you're able to recognize, we are dealing with a sorting center, and we have the information that there are some items for which we have a standard delivery, and it is indicated that amount of such items is 80%, while 20% refer to express delivery. So follow a following animation and try to catch up and answer the following question. So if you need, I just will say some blah 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 here, but I really hope that you catch up that unfortunately the model is not working correctly, meaning that a majority of the items should go to a standard delivery route or path, while a following model demonstrates us the totally different behavior. So after completing the first step, we could move to the second one, and the second step is validating model assumptions. We check if our structural assumptions and data assumptions are realistic. Talking about structural assumptions, for example, in a bank, do customers wait in one line or many, and are they served according to FIFO principle or by priority? We also check if our input data and chosen distribution make sense. So if we are happy, we could move to the next step. So the third validation step is input-output validation. We use real historical data as input to the model and compare the outputs with real KPIs. The reference can be the real system data or a trusted benchmark model. If inputs are realistic, output should also be realistic in a valid model. Okay, so let's consider the following simple example which we are able to understand and which we have discussed already for several times. We are talking about cash machine or ATM system. So just briefly to remind you of workflow, so we have a flow of the people who would like to get some service from the cash machine. What we did, we have collected the data about customers. We have collected the data about a service time, and they are numerical, so most probably we completed a model formalization stage, meaning that we have identified the distributions law for arrivals and service time, and of course we have developed the model. So the model can produce outputs, and of course it could be two types of, let's say, the output data of our primary interests. And here we could talk about, as example, ITM utilization, average delay, a maximum queue length, and it could be a secondary interest. At example, observed arrival rate, average service time. Okay, to continue the example, for validation we need the data from the real system or from a trusted reference model. Here we compare the model's average delay, so Y2, with the real observed delay, Z2, and as you're able to see, according to the slide, the real delay value is 4.3 minutes. A good model should produce results close to this value. Because the model is stochastic, and again, stochastic here means that there are random factors which are included, we run it several times. In this case, 6 replications, or sometimes in the literature you could find the word runs, so 6 runs were performed, and we have collected the data, you could see them in the table, and we are calculating average or averaging the result. Replications helps us to obtain more reliable and stable estimates. But the concept behind replications and runs is really very important. Therefore, as a next thing, I'm going to demonstrate you why we have started to talk about replications or runs. Okay guys, so just to demonstrate the concept of runs and replications, I'm going to construct a very simple model, and I'm going to demonstrate you why actually we need runs and replications. So I'm starting with putting the block executive, which, as you probably learned, is an obligatory element. Next I'm putting create block to the table, which would generate the items. The next one I will use activity to simulate some operations. What else I need is the exit block to simulate the exit from the system. Okay, and finally I need a block. Q. So here is the model which I got. So as you have already catch up, next one what I need is to link all the blocks together to organize the workflow. So let's just do a testing of the model. So I will switch on animation. I will run animation. Yes, it seems that the model is working. That's it. So now I will stop the simulation and I will go to at least, yes, let's call it 2 items. So I would like to see what are the input data. And I am starting with a create block, so pressing twice. What I will get the configuration screen for a create block. And what I wanted to check is a following part of a configuration screen, specify a distribution for time between arrival, and please pay attention, this one is really very important moment. It is stated here exponential, meaning that arrival process is a random process. Okay, we do not care what kind of parameters I indicated right now. Next one, let's go to activity block. Right now you are able to see that a delay is a constant value. So let's change it. Let's change it to specified by a distribution. We will get new options. Okay, and let's just again stick with exponential distribution. So let it be exponential. Okay, saved. So now what we have the model and we have provided the parameters. And again, sorry to be noisy, I would like to pay your attention that a rival process is a random process, and actually a serving process is a random process. So we have indicated exponential distribution in both cases. So now a bit more closer to the concept of runs. So first of all, I would like to pay your attention that exit block here has a value. So how much of the items we have processed. So meaning that if I will run the model, I would definitely see that a following amount is growing when the item is entering the exit block. Okay. So this one is a specific numerical value. Let me just switch off animation. Yes, switch off. And what we see that for a specific amount of the time, we have processed so much of the entities. Now, guys, here comes the magic. So now if I will rerun the model, so I will run the model one more time, but please pay attention, I am not changing any parameters. What kind of final result we will get for exit block? So let me press run. So it's already 10:06. Okay, maybe I could do a bit of zooming. So 10:06. And let's run the model one more time. So 10:37. One more time 10:35. One more time 10:28. One more time 978. One more time again 10:08. One more time 10:26. Okay, guys, I hope you catch the importance of completing several runs with the model, because we are utilizing distributions which are representing randomness inside the model. Each time when we are running the model, we are receiving the different results. So does it mean that a simulation model is not working correctly? Not at all, guys, not at all. So this one is just reflecting the randomness inside the model. And that's why to receive reliable results, we need to complete several runs for the model, for each experiment. But again, we are going to explore the topic about runs and the number of runs which we need to complete for receiving the reliable data in the next topic. This one is just the demonstration to explain you the overall idea. Okay, guys, now when you catch up the idea behind runs, I would like to go back to a slide which we have already discussed. And I would like to point out to a following very important statement, that the output from the model should be close to some specific value. Please pay attention that here we have replications. As it has been stated, we have completed 6 of them, and we have recorded the data. So what was the arrival rate, what was the service time, what was the average delays, of course, for each replication. So, of course, we could calculate the average value, but in this case, we have calculated average value or mean and the standard deviation only for average delay. And just try to see what kind of results we got. Just to remind you, we are talking that according to the real data, the average delay should be equal to a following value. Why? While we are receiving the following value. And here the question is it correct or not? Of course, we could recognize the difference, but unfortunately, we are not able to catch up. Is it close or it's not close to the specific value? Why? We are asking the question because additionally to the average value, you could see a standard deviation for a following mean value. So the question is still unanswered. So is it close or not to real value? So to answer the question, which is still unanswered, most probably we need to think about some techniques which would allow us to recognize if the value which we have calculated is close to the real value. And the first technique or first approach which we are going to discuss is something which is called a naive approach. Of course, the naive approach for model validation. And as you're able to recognize, in general, we are talking about calculating R-squared measure, but in the same time, we are also talking about creating the scatter plot for the data. So for what kind of data? So we are collecting information from the model. So we have a simulated data and we have a corresponding real data. So the dots are representing the data points. And as you are able to see, in a good case, I would call it, meanwhile, sorry, maybe it's a bit familiar statements, but in a good case, what we are able to recognize that our data points can be described with a line. And as I have stated, this one is just graphical representation, which works really very well when we would like to demonstrate the results of our validation to the stakeholders. But in the same time, we are also calculating a numerical value, which is called R-squared. So in overall, it should be stated that R-squared is a value which is from 0 to 1, and the overall message is that if R-squared value is higher than 0.7, so this one should lead us to the conclusion that the model is potentially valid. So a following approach is quick and intuitive, and it's useful for communication with the stakeholders, as I have stated. But it can also be misleading and even dangerous if used alone for decision making. That is why the naive validation should always be supported by the proper statistical validation and deeper analysis. Okay, so here is a numerical example regarding a naive approach. So we are applying the naive validation approach using R-squared. And as you're able to recognize, we have a small table which represents the output data from model 1 and the output data from model 2, and we also have a corresponding real data. And just to remind you, our goal is to understand if the model demonstrates the realistic behavior. So for model 1, R-squared is only 0.28, which is far below the threshold 0.7, which we have identified. So this model clearly fails the naive test, while the second model demonstrates a bit different behavior. So R-squared in this case is equal to 0.86, which looks very good, and the model appears acceptable based only on R-squared measure. But again, the key point is that a high R-squared alone does not prove the model is valid or not. It only shows similarity, not a correctness. That's why, again, sorry for repeating, a naive approach is really a very simple one, as it also provides some visual, I would say, visual output. It can be used to demonstrate the result, but in any case, you should consider to use much more complex statistical procedures to be sure that a model is valid or not.